Hello and welcome to my video. I've noticed that this coronavirus crisis has put a lot of respirators for treating patients on the needs list, and everyone's trying to find a solution to this crisis. I was thinking uh, before mass vaccination or an adequate medicine for this virus, the first problem we can tackle with is producing faster and more affordable respirators so that the patients can afford one at home and treat themselves, and in this way not overcrowd the ICU units in the hospitals. This is my design of the most simplest, easiest to manufacture and comprehensible respirator. I'm going to go through the steps of explaining how it works, what is the logic behind its design, and some tips on how to mass manufacture a device like this. So first, we're going to explain how it functions. This is the valve in which the air goes in, and this is the valve in which the air goes out. This is the actual pump, and this is the motor and a simple interface to set how the motor works. We're going to explain the pump first. This is your basic thread pump. In here, these cylinders turn, and because they're touching the walls and each other, the air is going to be pushed in the direction of which the cylinders turn. Because they have to be synchronized in turning, they have these gears that synchronize them, and also because they have to turn, they have these pivot points on which they turn. This is the engine that's going to turn the first cylinder. The first cylinder is going to turn the second cylinder, and the air is going to be sucked in this valve and be pushed out this other valve. Because this is a concept stage design, it's not the final stage, I have sketched out as simplest as I can to explain how this device is going to work. The most simplest interface I could come up with. The second cylinder is going to spin a thread. The thread is going to be pushing on this indicator all the way to the left, where the indicator is going to touch the setter, and the rotation of the motor is going to be reversed. Then the air is going to get sucked on this valve and be pushed out this valve. In this way, this device can push air into the lungs and take the air out of the lungs. This setter is adjustable, and we can adjust how much air gets pushed into the lungs and gets sucked out. And because this is an electric motor, we can adjust with the current going into the motor the speed at which the air gets pushed into the lung and sucked out. So we have two parameters here, how much air goes pushed into the lungs and sucked out, and we have this setter that sets the volume of air that gets pushed in and sucked out. To better explain how this works, I have an animation. And this is the engine turning the cylinders that synchronize on the gears. The second cylinder is going to twist the thread that's going to push the indicator all the way to the right, where it's going to make contact with the setter, the adjustable setter, and then the motor is going to inverse the rotation, and now the air is going to get sucked out from the lungs and pushed out into the environment, while the indicator goes all the way to the left, and this process is repeated. And here we have an example of the setter being pushed to the left, being turned because it's sitting on the same thread. And as an animation, this is a shorter frequency of the motor running, and it gets inverted faster. This is going to be a smaller volume of air being pushed and then sucked out of the lungs. Uh, this setter is going to adjust the respirators from large volume lungs, like adults have, to small volume lungs, like children have. And in this simple way, we have a volume of air that gets pushed into the lungs and a manual setter that sets the volume that gets pushed in and sucked out with just the setter. Now in this particular example, notice there's no bolts or any means of assembly these components. They can be glued together or bolted together. The material is mainly plastic because it can withstand the forces that are involved in the operations of this device. For example, I'm using a 25 diameter cylinder with a 5 mm square profile that adds up to almost 3 centimeter cubes of air getting pushed per rotation. This is a lung capacity diagram I found on the internet. We're breathing with the capacity of the tidal volume of the lungs, which is around 500 centimeters cubes. But we also have an expiratory reserve volume and an inspiratory reserve volume that total up to 4,500 centimeter cubes. So it means that this engine should be running for 70 to 100 rotations per second for the tidal volume to almost 500 revolutions per second to include the inspiratory and the expiratory reserve volume. And this is an electrical diagram of a reversible DC motor in which I've explained the phases between forward and reverse here on the left. The indicator is going to start moving forward, and when it reaches the setter, it's going to stop and reverse, and then slide all the way back to the initial position where again it's going to stop and forward and set the frequency of the motor functioning in between pushing the air into the lungs and pulling the air out of the lungs. And this is my sketch of an electrical diagram adapted to the device I've designed. So here we have a plus minus continuous current voltage that is going to be referenced to a plus minus on a microcontroller. This microcontroller is going to have a plus minus output, and this plus minus output is going to be reversed on these two indicators here. Down we have the sliding indicator that I've shown into the design. That's going to slide from the left to the right to the adaptable setter, and it's going to invert the plus minus all the way to these two-way transistors, PNP transistors, that are going to reverse again the current into the coil of the motor. I went for a microcontroller because it's going to provide the possibility to stop and reverse every time the current, so that the inertia on the motor is not going to be high, and also the airflow into the lungs isn't going to change direction abruptly and provide discomfort to the patient. This has been my concept design of a mass manufacturable respirator in response to the coronavirus crisis. I hope you enjoyed this video, and remember to have fun at work.